Hi everyone, I'm ADITI, that's SANDOSH. Thanks Jesse for introducing us. We both work at Zillow Group, and today we're here to talk about caching all the things, aka how you can delight your customers using GraphQL and different caching techniques to scale that GraphQL. But before we dive into caching, Jesse, the slides are not showing up? Technical difficulties indeed.
Yeah. They are up now.
Thank you. So before we dive into caching, let's set up the stage a little bit. So today's use case is based on Trulia, which is a brand owned by Zillow Group, and it's also one of the first teams to implement GraphQL at scale. So Trulia is an app or a website where you can go to find your dream house. You can log on to trulia.com and look for houses based on different criteria, like amenities, restaurants in the area, schools, places with less crime. After all, nobody likes the idea of getting mugged. So let's look at a page on Trulia. This is a property on Trulia. I am totally digging the staircase, very Victorian. And as we scroll, $25 million? Guys, this is a steal. In Pacific Heights, San Francisco, a 4-bed, 4-bath. For all of you that aren't from here, that's a pretty good price. Under that, we have some local information, a map view, schools, crime. They all have little blurbs under them, and you can click onto any of those cards for more info. Then on the other side, you see a form. And if you want to connect to a listing agent or an agent that can show you this property, you can fill out that form. Underneath that, there's a description. And as we scroll further, there's a price history for that property. So whenever it was listed before on the market, what it sold for. And finally, if this house doesn't catch your fancy, there are other homes like that that you can buy or check out. So now that we've seen a page on Trulia, how is it powered? Our tech stack looks like this. It's Node with Express and Apollo client. We use that to talk to our GraphQL Apollo server. And the page actually lives in a Next.js app, which is written in TypeScript and React. So we actually have 2 different web apps and 4 pages split between them. And they all use a common GraphQL server along with our other clients, Android, iOS, to talk to 20 different REST APIs for different categories of data. These web apps and our GraphQL server are deployed in our Kubernetes platform, while the REST APIs are all over the place. So some of them are in AWS, some of them are in our data center, and actually some of them are third-party. But let's talk about the GraphQL piece more. So the way we use GraphQL is like an API gateway to all our REST APIs. It takes the request from the client, gathers all the data necessary, transforms it, and sends it back. I'm going to do a quick poll across the room. How many of you use GraphQL in a similar fashion to ours, which is like a middle layer? All right, I see a lot of hands. That's good. How many of you use it purely to talk to your databases? Fewer hands. OK, so I'm guessing the rest of you either use it for a combination of both, or you don't use GraphQL at all, which is fine. But our talk is most relevant when you use GraphQL as a middle layer to access different REST APIs. So how is it set up? In our setup, we have the GraphQL server on one end, which has the connectors, the common error handling logic, the logging logic, and the middleware for the servers. On the other hand, we have the data sources, which pertain to a different category of data, separate categories of data. So there's crime, schools, there could be one for amenities. And what happens is the GraphQL data sources are taken as an input to the server, and the server then forms that middle layer. So on the right-hand side, you can see that there's a pattern called the connector model resolver service pattern. It's quite common in the GraphQL community, but let me run through it quickly once for all of you. So the client app makes a request to the server. The server passes it on to the resolver for that particular data source. And the resolver knows what schema fields that are requested map to what function calls in the service. So it queries the service or that function in the service for the data. The service doesn't make a call to the backend API on its own. What it does is it passes it to the connector in the data source. The connector in the data source is basically a shell that extends the REST connector in the server. And why we chose to do that, we'll talk about in a bit. The REST connector in the server reaches out to the backend API, gets the data back, and then it passes back in the flow. A model is created with the relevant data, and then the resolver gets it and returns the fields to the client app. So now that we know the data source pattern, let's zoom into the REST connector, which lives in the server. What it is a generic utility that's a wrapper over Axios. Axios is a popular JavaScript library to make HTTP calls. And all our retry logic, performance marks, and other metrics that we want to gauge, all of that is done in the REST connector. And the benefit of it is that every data source doesn't need to implement their own logic in their connectors. So we were looking at this repository structure before, and we have different data sources. Let's look at how the crime connector uses the REST connector. So the crime connector just extends the REST connector and passes in a URL to the crime API. So if we need to pass in any custom headers or some more configuration is needed to access the backend server, the general REST connector handles that. So we have a picture of what a page looks like on Trulia, what our tech stack's like, what the infrastructure is like, and also how we make calls to the backend using GraphQL. Let's look at that property again. What I want you to notice are the numbered circles. They pertain directly or map directly to different REST API calls. So number 1 on there is a REST API call to get the nav bar. 2 is to get that picture that I really liked, the description of the property, and stats about the property. 3, 4, 5, 6 are local calls for local information, so they're all different REST APIs. 7 is to get the listing agent data for that property. As we scroll down, 8 is to get the market listing details of that property. And finally, the last call we're making is to get the similar homes to this property. So we saw that one call coming in for this page led to 9 different REST API calls. In reality, we have a lot more data on these pages than I just showed you. So it translates over to 20 different calls to 20 different backend APIs. And honestly, that's not scalable. So maybe SANDOSH will now talk about some of the challenges we faced and how we decided to solve them.
Thank you, ADITI, for setting us up, giving us an overview of how we do GraphQL at Trulia. Let's take a look at this page again. One request coming into GraphQL becomes 20 plus requests going to backend APIs. This is just one example of a query. If we were to scale this to 3 million or 5 million requests, that's going to be very challenging. And it's going to be especially challenging at the infrastructure level. When we look at DNS lookups, TCP connects, those are the few areas we looked at on how to optimize it. But we kept asking ourselves, are all these requests that we're making to backend APIs, do they all have to be real time? And we ended up with the answer, no, not really. Only some of them have to be real time, but most of them don't. So we set a goal for ourselves to reduce the number of outgoing requests from the GraphQL server to our backend APIs. And to do that, we looked at 3 areas. 1, the GraphQL server itself, primarily at the resolver level. 2, at the HTTP layer. And 3, at the DNS layer. And we came up with these solutions for those. Data loader. How many of us use data loader in their stack today? Great. And Varnish for the HTTP layer. Are there any Varnish users? All right. And for the DNS layer, we used a DNS cache. For the first layer, data loader, let's see what it is and how it helped us cut down on the number of requests we made. And to do that, let's look at this very simple query, where we're requesting homes, and we're asking for some fields for each of those homes. And we know resolvers in a standard setup are very simple functions that just makes a query or a request to a backend API, gets data, returns it. In this case, for the root level homes, it's going to make one request, get data for homes, return it. But it might not have data for the address field. So then it's going to make another call, maybe just not one, but it's going to make n number of requests for n number of homes. And this adds up. And if you want to make another field, or if you want to add another field, let's say you want to ask for mayor of the city that the home belongs to. I don't know why we would need it, but let's say we needed it. It's going to make more requests for each of the cities that each of those homes belongs to. And it's a classic n+1 problem. And this doesn't scale. And it's a problem because resolvers are very simple functions, or could be very simple functions. And they're not aware of other resolvers. And they only have access to their parent object. This is where data loader comes in. It's a very generic data fetching layer utility. It provides batching as a core feature. At a high level, all it does is collects the keys that are being requested in a given event loop tick. It's going to make just one request to the backend API for all the keys that were requested. And it's going to return a promise that's going to eventually resolve to a collection of values. And all you need to get a data loader working is a batch function, which kind of looks like this. It takes an input, which is an array of keys, and returns a promise that resolves to an array of values or errors. And it's important to note that it returns a promise, and it's not trying to resolve the fields or the data right away. This really helped us cut down on the number of calls we were making, because at times you were just making the same calls from different resolvers. So this way we were able to batch it. Another feature the data loader provides is cache memoization. So for any key that gets requested, data loader caches that value in memory. And it does that on a request basis. So they're not shared between requests. So for any new request that comes in, it's not going to be able to access that data. And that's where we looked at how to do caching in the HTTP layer. And for that, we chose Varnish. And Varnish is an application accelerator. It's also known as a caching reverse proxy. It speaks HTTP, so you can put it in front of any HTTP server. It can speed delivery up to 1,000 times. It's been used for many, many years, maybe even a decade. And it's highly performant. It's very easy to tune. And the reason we chose Varnish is because we wanted to bring GraphQL, or the cache, closer to GraphQL server. ADITI mentioned that we have our backend APIs all over the place. Some of them in our Kubernetes cluster, some of them in different AWS accounts, different networks, but in some cases they're third-party or even in a remote data center. And we also wanted a way to experiment really quickly. We didn't want to go to the backend APIs to change any of the cache values or cache configurations. We could just do that at the Varnish layer. And those cache configurations can be overwritten by response headers. So that was really easy to test and play with. If you go back to this diagram, we're using GraphQL as an API gateway in front of our REST services. And with Varnish, it looks kind of like this. So we provided Varnish instances for each of the backend APIs we were talking to from GraphQL. It might not be clear from this diagram, but Varnish is much, much closer to the GraphQL server than it is to the backend APIs. And the way we use it in our code is very easy. We saw this earlier where we specified the base URI for a REST connector and crime connector in this case. And all we needed to do to add Varnish capability is to add an API cache base URI and point it at the Varnish instance. And with this, we got a lot of features automatically. It had support for fallbacks. If the cache wasn't available or if Varnish is down, it can fall back to the origin API. It can also do some retries. Let's take a look at what happens when a request comes in to Varnish. So this is the first request GraphQL is making to Varnish, asking for a resource, and Varnish doesn't have it in cache. It's going to make the GraphQL server wait until it fetches the data synchronously from the backend API. And once it gets a response, it's going to store it in cache and return that data to the GraphQL server. And every time it caches an object, it's going to set that value TTL, which is time to live. And it defines how long a cached object is stored before it's purged. And for any new requests that come in after we have it in cache, Varnish is going to respond really quickly, and GraphQL server gets the data right away. But when the cached object expires, it gets purged, and a new request comes in, Varnish is going to make the GraphQL request wait, get the data from backend, and return it and store it. And this cycle continues. But we notice that there is a optimization point there where Varnish is making the GraphQL request wait while it fetches data synchronously. So we added support for this feature called grace mode. It comes with Varnish. What it does is it extends the life of the cached object, so it can live a little bit longer. And during that time, when Varnish gets a request, it returns the data right away, so GraphQL has it. But then it asynchronously refreshes the data on the background. This way, the data is kept fresh, but it also returned to GraphQL as soon as possible. This is great, especially when everything is working fine. But what happens when there's a downtime in the backend API? A new request comes in, Varnish returns the data right away to GraphQL, but it tries to refresh that data from the backend, but it fails. There is some connectivity issue or backend is down, but Varnish is going to keep trying until it gets the data. But sometimes it will not happen. In that case, when the cached object expires, Varnish will return a 503, and the client can handle that scenario. Now, this was really helpful for us because GraphQL was shielded in some ways from downtime of our backend APIs whenever that happened. And the way we deployed Varnish was also very easy. We did this in Kubernetes, so all we needed were these 10 lines of code, and we could specify TTL and grace period right there, 7 days as default for this instance. And within a few minutes, we had Varnish up and running to experiment. And to override those values, all the backend APIs needed to do was specify this cache control header. In this case, max age set to a year, I think, that overrides the 7-day value. And to override the grace period, it had to specify stale while revalidate header as part of the cache control. Now, this is a draft proposal. I think it's not standard yet, but Varnish supports it, and some other providers also support it. So we saw how we implemented cache at the GraphQL layer, at the HTTP layer, and to talk about what we did at the DNS layer, Aditi.
Thank you, Sandosh. So in the beginning, Sandosh showed you this goal, which was to reduce the number of outgoing HTTP requests. With Varnish and Data Loader, we were able to scale our performance to 13 times its original performance marks. But that wasn't enough, because engineers love stretch goals. The stretch goal was reduce the time spent in one HTTP request. And this is what a lifecycle of an HTTP request looks like. So in the beginning, there's a DNS lookup that's done by the DNS server, which is basically finding out the address or the place where the backend API it should connect to lives. The second part is connecting to that backend API, which is the TCP connect portion. And after that is the data transfer. So the TCP connect can actually take a long time depending on where the server is, whether it lives in AWS, whether it's third party, or whether it's in an old data center. So to maximize performance here, we actually just used Node's HTTP agents configuration and enabled the keep alive option. So what it did was it established a connection for the first outgoing request to that server. And all the subsequent outgoing requests use the same connection for data transfer. It was easy to reduce the time here. What was hard was the DNS lookup. I think it was hard because initially we didn't even know we were spending a lot of time on the DNS lookup. When we profiled our GraphQL server, we found out that we were spending more than 10% in the DNS phase. So into the code we went. This is the DNS server we use. It's called CoreDNS, and it's written in Go. All the functionality is outsourced to plugins, so it's easy to remove something or add something, and it's very simple to configure. So in our setup, you can just define core files, and these are how they're defined. So here we're telling CoreDNS all requests to apis.trulia.com should be forwarded to 9.9.9.9, so a different DNS server. And we can also turn on DNS logging, like every query is logged, by adding the simple word log. So when we decided to do caching on this layer, it turned out to be really, really easy. All you had to do was define a cache block for your servers. The cache block here is read as follows. We decide what to cache, and then it's the capacity of packets to cache, and an optional time to live in the end. So here we're saying requests that are going to apis.trulia.com, the successful name resolutions, please cache 5,000 packets of that for the default TTL, which is 60 minutes. Then we're saying denied resolutions or failures to reach the server should be cached for 300 seconds and 2,500 packets of that. And finally, here is where CoreDNS shined and we saw the magic, was we're telling it to prefetch 2,500 packets of the name resolutions CoreDNS thinks we're going to use next. Let's recap all those solutions really quickly. The first one was Data Loader. It's the least barrier to entry solution because you can change things in your code. You don't actually need any new infrastructure. The second one was Varnish, which was between GraphQL and your backend APIs. In our case, we put Varnish really close to the GraphQL server, so we wouldn't have any dependencies on those APIs. Instead of Varnish, you could use a different set of options. Fastly is something that's also really popular right now that people use between GraphQL and their services. And the last thing was DNS caching, which we profiled and found out was a problem, and we fixed it by caching on that layer too. If you have any questions about anything, tweet us on these handles. We're also available on Gmail at these handles. Finally, Sandosh and I are hosting a topic table on caching. Come join the conversation at lunch. I know we can't compete with puppies. We'll try to make it interesting. Thank you, guys. You've been a great crowd to present to.